In this video, we'll talk about general exponential functions and general logarithmic functions, differentiation, integration problems involving those functions. At the beginning, we want to point out that because the derivative of log is 1 over x. That's one of those basic differentiation formulas we learned in calculus. So if we integrate both sides, then we end up with a new definition of natural log. So with this new definition, we can verify all those logarithmic properties we discussed in algebra, like log of product equal to sum of log of each. So we use basically property of integral. We'll be able to verify that and many others. This is a calculus course, so we are not going to spend much time talking about the algebraic properties of function introduced this way. Anyway, with the new definition for natural log, we can define also inverse of natural log as natural exponential this way. This definition is for exponential to base e. And this is how we always define inverse of a function. Given log, we define inverse by switching x and y and call function defined implicitly this way as exponential. Now, like I said, this is a calculus class, so we will primarily focus on integration differentiation involving those functions. Now, the log here is log to base e, and the exponential here is exponential to base e. That's not what we're talking about in this section. We already learned how to differentiate exponential to base e, or more general exponential expression to base e, and the logs to base e to base e. What we want to focus on is what's called a general exponential, general logarithmic. Like a to x. Well, the base is an arbitrary positive number, or log of x to base a. What we want to learn here in this section is we don't need a new set of formulas for derivative of general exponential expressions, or derivative of log to general base. In calculus 1, we had all those formulas already. Now, with what's called change base formula, this is exponential to base e, base b. I'm sorry. The b can be any positive number. Now, the change base formula says this exponential equals a new exponential to a new base e. Now, the new base doesn't have to be e. It can be actually any other positive number. then we would have to coordinate the log to the same base. As long as the base e here and the base involved in the log are the same, this identity holds. Obviously we want to get the natural number e involved because of the formulas available. Same reason, general logarithmic expression to base b can be turned to an expression involving natural log to base e. The reason again is obvious. Since we know differentiation formulas for natural log, so we want to just make use of those formulas. This way we don't need differentiation formulas for exponential to any other base, arbitrary base, or differential formulas for log to any other base. Alright. Okay, let's see some examples. Say we have an exponential expression y equal to 2 to 1 over x squared. How do we find its derivative? Well, I'm going to show you we don't need any new formulas. The old formulas plus change-based formulas are all we need. Okay, first of all, let's change the base. So let me copy down the function. Then change the base. I'm going to change the base to e because there are differentiation formulas involving base e available. Compared to the formula, change base formula, then have the new base e, the original exponent is like a, so I'm going to just copy it down. Have log of 2 there. 2 is like the b in the formula, so 2 will go into the log in the new exponent. That's how we change base. Now you see the right hand side, it's just like standard familiar exponential expression to base e, so we're going to simply use this formula. It's called general exponential rule, or it's basically general plus the basic exponential rule. Anyway, we apply formula. So this is like f in the formula. We'll have e to f log 2 times f prime. Just set up first. This thing looks kind of complicated. It's a fraction, it's a product, so we're going to focus on derivative of this next step. This part, copy down. Now, how do we differentiate this? Well, log 2 is just constant coefficient, so we can just copy down. Where 1 over x squared, you can apply reciprocal rule, you can apply quotient rule, better rewrite it as power. You apply simple power formula. Negative 2 down, subtract 1 from the power, so it's negative 2 over x to the third power. That's an answer. This expression is the equivalent expression for the original exponential. Now, you don't have to turn this back to that. If you check the answer in the book, for a problem like this, they may have this. It just means they turn this back to its original form. See, these two are exactly the same thing. You don't have to do that. This is fine, in my opinion, because it's much easier to evaluate the expression involving natural number as a base in exponential. Okay, but anyway, either one is fine. So you can see here, to find the derivative of an exponential function to base 2, we didn't need any new differentiation formulas. Just the old formula plus change base formula from algebra 2. Alright, next let's see a problem involving logarithmic to general base. Well, actually two of them. There's a base 2, there's base 3. So how do we find the derivative of this function? Change base. Okay, you'll see, as long as we know how to differentiate the natural log to base e, we have no problem working on any log to any base. Alright, so let's first, well, there's a base 3, there's base 2, we need to change both. Let's change base inside first. Well, this is the change base formula for log. So we can choose a new base. We're going to choose a natural number as the new base. So it's a log of this part and the log of the base, original base. According to the formula, we have them natural log of x over natural log of 3. Alright, so that's inside. Now outside, let's take care of this base. Similarly, we're going to have log of the inside log of the original base. So we have now is a fraction involving only natural log everywhere, but that's okay. A lot of them are constants. Okay, so we could differentiate now. I would simplify the top a little bit. You'll see we're going to apply a property of log to turn this into a simpler expression. There's a property in log that says for any log a over b, fraction inside is log a minus log b. This is the property going to use to simplify the top. So log x is like the capital A, log 3 is like capital B. So I have log of x, log of log x minus log of log 3. So this is like capital A, this is like a capital B. This way it's much easier to differentiate, so we don't have to worry about the top being composite function with a fraction, that kind of thing. Okay, so this is so far all algebra. Now we're ready to differentiate. Notice the expression is a fraction, but the denominator is a constant, so it's like a coefficient, 1 over log 2 in front, log x minus log 3. Okay, now the expression inside the parentheses is not that bad. This term basically is a number. You'll see, the root of that is going to be 0. So all we need to worry about is the root of that. Anyway, so let's start to differentiate. 1 over log 2 is a constant factor called coefficient. Just copy it down. Inside two terms, like we noticed, this is just a constant, so derivative of this term is 0. The only thing really we need to differentiate is log of log x. Now we apply this formula, log of log x. So we have log x here, log x here. Okay. It's 1 over log x times derivative of log x minus 0. So the log x here is like f in the formula. Alright, finished up. Log 2 times 1 over log x times that. It's pretty simple. And this is 0. So final answer. So we start with a rather scary looking expression, log inside log, with general basis, 3 here, 2 here. That turns out it's no big deal. Just change the base and differentiate. We didn't need any new differentiation formula. Alright, these are differentiation problems. Now let's see some integration problems involving general log, general exponential. Okay, so how do we evaluate this integral involving exponential to base 10? Simple. Change base. Remember how we change base? We're going to have, of course, the preferred base natural number. Copy down the original ln 10 dx. Now we have a new expression involving e to something, familiar exponential. From here, we obviously need to regard this as a new variable and try substitution. So let's try this substitution. Okay, du equal to log 10 constant 1 over x squared differentiate is 1 over x differentiates negative 1 over x squared dx. So we see in this identity dx over x squared equal to negative move over log 10 divided both sides. Alright, so the combination of dx and x squared on the bottom becomes that. This says the original integral becomes e to u, and this combination, according to our identity on the side, is negative du over log 10. Okay, let's finish this one. Negative log 10 move to the front, it's constant, so it's just a very simple integral. Integral of EU is just EU plus C. Now finally, E to U. So that was U, right? Alright, this is how we evaluate integral involving exponential to some arbitrary base 10 in this case. Could be any base, but all we need to do is to change the base. So we just treat the integral just like before. Okay, whatever we have to do. In this case, after changing base, we realize we probably had to try a substitution. Alright. Now, from the change base formula, this expression is the same as 10 to 1 over x. You don't have to write this back as that. This is fine. Again, if you look at the book, they probably have this as a final answer. Either one is fine. Alright, let's see another example. This is integral involving log to base 2. Okay, change the base first. So it's log this part over log of 2. From here, let's move out the log 2 because it's constant. So we now obtained integral that we ran into before. And actually, it's a pretty simple one. We'll try substitution again. U equal to, say, log x. So du equals derivative times dx. Log x becomes u. According to the differential identity on the side, says 1 over x dx, same as du. So this part is 1 over x dx becomes du. A very simple integral. Power. And finally, you get the log x squared. Final answer. So from these two examples, you see, doesn't matter, whether it's exponential to arbitrary base or logarithmic to arbitrary base. All you need to do is change the base. Change the base. This is how you change the base. Any base to base e. Any base in log to base e. So you have a natural log. Alright, so to do differentiation or integration involving general exponential, general logarithmic, we don't need any new differentiation formulas. Just change base. In the textbook, you can find actually they provided differentiation formulas for general expression, general exponential expression. Like I explained, you don't need that. If you want to actually have a formula, you can derive it for yourself. For example, you may find the derivative differentiation formula for that. See, it's up to you. You want to have it. You can use the formula in the book, or you can derive the formula for yourself. Like in this case, I would change base, and that's how it's done in the book. Change base to e to x log a. Then apply the formula, copy down, times x log a. Then this becomes e to x log a. Log a is a constant, copy down. Derivative of x is 1. So they have formula like this, or actually write this back as a to x. So you may see the formula like this. So in the book they said a to x prime equal to log a times a to x. They call the formula. Of course, you can accordingly come up with other formulas like expressing a to f of x or log of x to base a, log of f of x to base a. Just change base. You just change base and you can derive all those formulas for yourself. Well, in my opinion, they are not needed because we could easily deal with differentiation problems or integration problems as shown through these examples with existing formulas. Those guys plus change base formula. Alright, so to summarize, in this section we learned to differentiate and integrate general exponential functions and the general logarithmic functions. No need for any new formulas. Differentiation formulas from calculus 1, change base formula. Alright.